All right. Today we're going to start, complex numbers, but really complex numbers, right, really relates to frequency and energy storage. All right. Real, right, just doing this, right. Um, the voltage here is the voltage division of whatever the input is, and with ideal components, they're all real. There's no delay. All right. Um, so the input might be time varying, but there's no time delay between the input and the output. All right. With imaginary, right, that implies a capacitor or an inductor. You can have delay, or you can have a frequency response. The frequency response of this, well, it's just constant over frequency. It doesn't really change. All right. Power, right, is equal to V squared divided by R, or I squared times R. And this is real, not complex. All right. What is something complex? Well, the impedance of a capacitor is 1 over SC. And when we talk about frequency, we let S equal J omega. So we get 1 over J omega C. ZL is S times L. And when we substitute J omega, we get J omega L. So that imaginary component, it comes with the frequency component, right? Now all of a sudden frequency is in there, right? And because it's imaginary, right, or we're storing energy, there's no power dissipation. Now, so an ideal capacitor, right, it's all imaginary, right? Ideal inductor, same thing, right? Now, right, this is an ideal resistor, right? But the thing is a real resistor has real parts, right? There's a wire, then you have this kind of bubble-like thing with, you've got your color codes and things like that, right? This is really physical. And so a real resistor will have non-ideal components attached to it. All right. These wires have inductance. Like from physics 51, right, you have Maxwell's equations and a wire has inductance, right? If I have something, if I'm separating charge, I'm going to have capacitance, right? You know, an ideal capacitor, right, also has the capacitor, but there's some leakage past the capacitor and the leads have inductance. And of course, an inductor isn't just an ideal inductor, it has a resistance. I'm just going to put the capacitance here, but these are just like the simplest models. Or maybe the capacitance can be across both of these or across the resistor. All right. So back to what I had said earlier, if I have a time varying signal, right, and two resistors, and I say, hey, there's no time delay because it's all real, right? There's no delay in it. Well, in fact, right, the non-ideal inductor capacitance will make it that there is a delay between the input and the output. But when a lot of times when we're analyzing things, we keep it all ideal and then add in the things that that are important. And also, let's say we're doing this kind of thing, is that even though this has inductance and capacitance, and this has resistance and inductance, this resistance and this capacitance are like the dominating feature. All right. But when you get up to high frequencies, yeah, these parasitics can be important. So complex, right, has real and imaginary, right? Real is just like a resistor, an ideal resistor, and imaginary would be ideal C or inductor. But when you combine them together, we get a complex number. Now, just so we define ourselves, all right, and we're going to use this a lot in 110. You have an imaginary plane axis and the real axis. So everything here this is plus J minus J, and the complex, sometimes numbers have the real part plus J omega. Because so often that we're dealing with frequency and things, rather than just label it J times something, in fact, that axis is frequency when we actually go and try to measure something. So yeah, complex number. Right, I can have something here. I can have something here. Here. Right. And we have our Cartesian coordinates, right? So X is going to have some positive real number plus something like that, right? The blue has a negative real number plus some real imaginary number plus some plus some imaginary number. The black is in that third quadrant, so everything is negative, right? And then we have, right? And so the real plus imaginary, that's the Cartesian coordinates, right? But a lot of times we're going to use a magnitude and phase. And the reason why I'm kind of going over stuff that, I know you already know, but we just need to make sure we're all on the same page, is that adding and subtracting, right, complex, it's better to use Cartesian. Multiply and divide, you want to use polar. Now, yep, it's true. You can use your calculator, right? Just most calculators have some kind of complex number in it. But when you really need to get the right answer and you want to, I have this number and this number and I want to add, right? You probably want to draw it out just to say, oh, I have, this is where this one is, this is where this one is, right? If I'm going to add them together, right, what'll happen, so that, I guess what I'm saying is it's really prone to mistakes. And so drawing a picture is a really helpful way of going about it. So, if we look at this, right, we want to find the equivalent impedance, all right? And yeah, I could just put A here and say we have a resistor in series with an inductor and then a capacitor in parallel. Well, that's like maybe it's a non-ideal resistor or a non-ideal inductor or a non-ideal capacitor, but we would be finding out what the impedance of that whole area is, all right? Well, you don't really have to learn anything new from what you know about resistors in series and in parallel. So Z equivalent, well, we've got a parallel branch, but right, it's the impedance of the resistor plus the impedance of the inductor, and I'll put it parentheses, right, in parallel with the impedance of the capacitor. Now, from the problem, ZR equals R equals 5 ohms. ZC equals minus 11, but notice they put the J here, right? and the units are ohms. ZL is X1, that's 2, but it's 2 times J. Oh, excuse me. All right. So ZR plus ZL, that's easy, right? Because we're just adding things together. These are effectively in Cartesian already, because that's 0J plus 0 something real plus 0 something real. They're already in Cartesian. So we get 5 ohms plus 2J. All right. Now, that is all in parallel, and we'll just remind ourselves what it is. I'm just going to scroll down. It's all in parallel. All right. Now, it's helpful just to remember the parallel combination of resistors. So I have ZL plus ZR times ZC divided by the sum of the two things. All right. Yeah, at this point, we got to start using our. So ZR was 5. ZL was plus 2J. ZC was minus 11J. And then we have 5 plus 2 minus 11J. Five minus 9J. Over here we have 5 times minus 11 J. Here we have plus 2J times minus 11J. So we're going to have 22, right? We know that J times J is in fact minus 1. Minus 1 times minus is plus. So we just leave it at 22. And this would be ohm squared, ohm squared, ohm, ohm. So all the units would cancel to ohms. Now, yeah, you can put this in your calculator, and also you can kind of use the complex conjugate way equation of keeping it in Cartesian. I think it takes a little bit too long. So what I like to do is convert things into polar coordinates, right? Now, but before I do, I like to make sure that I know what I'm doing. So if I go out 5 and down minus 9, right, I'm going to be here somewhere. So that I really should have some kind of minus angle, right, between 0 and minus 90, right? This one, it's 22, 55. So again, I'm going to have some, I should have some kind of angle, so a magnitude and an angle that is in this quadrant. And you have to make sure that, because when you get out into these quadrants, it won't do it. It actually only gives you between here and here, and you've got to make sure you back calculate what it should be, right? If your angle's out here, it'll give you this angle, and you have to realize, oh, I was in this quadrant, and take care of that by adding or subtracting 180 degrees. So we need to put that into magnitude, phase, magnitude and phase. So the first magnitude, right, 22 squared plus 55 squared. Okay, we'll do the next one. All right, and you got to make sure, like, are you in degrees or radians, right? Because if you were in radians, you'd come out with some really small number that wouldn't make sense, right? So we'll divide things out. All right. So we're going to have a magnitude and a small angle. So we should have a plus real and a negative imaginary part. And if we've done everything right, there should be a number really close to that. Oh, let me grab the answers. Okay. So 5.68. So maybe it's this one. Right? But also maybe it's this one. Right? Because these are all kind of close. It's definitely not that one. Right? Now, we have a minus number here. So that's plus. Can't be that one. Can't be that one. So we are left with these two. Oh boy. Well, it looks like I probably should have used more digits of precision. And what I tend to do is in my calculator, use all the digits of precision. I don't know. This one looks closer to this one. And I'm going to say well, that was wrong. So then is it the other one? Okay. I wouldn't want so some of these they're really close on purpose. All right. So I mean, in order to get access to the test, you were supposed to listen to my little speech on the exam, and there's things that are distractors, right? So we're here, right? So I give you the same number, positive. I'm giving you answers that are here and here. So like you don't know, is it this one? Like this one has the negative one, that one has the negative. But if you've done something wrong, well, yeah, the distractor is an answer that you might calculate, right? It's the dirty trick, right? That's what a distractor is. And then, yeah, sometimes there's a wild answer that's just not even close. They're programmed, though. And yeah, why is 5.66 versus 5.71? Might not seem like a big difference. But yeah, I really should have taken 2 digits of precision, 2 digits of precision all the way through. That was I'm a bad person. Because just so you know, trying to make those questions with the answer's always some whole number with distractions that are always some whole number. Sometimes you can guess the answer, right, just from that. So sometimes you have to that's weird. All right, I don't know what I was thinking. Yeah, so we can see that. That was pretty close. Yeah. So 2 digits does the trick. All right. So these are all in the AC. That's the first one. Then converting this to polar. Right. You have different things that you have to sum. Now here we want to find the Thevenin equivalent, but we've got a current source, right? And that current source, you might be thinking, you might forget it's a current source and say, oh, that's just voltage division, right? To find a no, that's to find the voltage. But what you might think is, oh, short this, and then this will be in parallel with that. But that's not the case. To set that current equal to 0, you take it out. You put in your test current, and this is infinite resistance, so no current flows in that branch. So really, Z Thevenin equals ZC equals X2, right? So minus 5J. All right, because remember the Thevenin, or you set the inputs to 0, send in a test current, right? Make the load, take away the load, and then see what the voltage happens to be. And V Thevenin is actually kind of easy here as well, because this current source, all of these are in series. The voltage is just that current times that impedance, right? It's not part of the question, but V Thevenin is really just IS times ZC. IS is 8 plus 0J amps. ZC is minus 5J. So V Thevenin, right, is 8 times minus 5 is minus 40J volts. Or 40 minus J is minus 90 degrees. The magnitude is always positive, right? So plus J is always plus 90, right? V Thevenin isn't so important for 110, But really, the manipulating of these variable, the complex manipulation and adding and summing capacitances, that's the big part. Now, yeah, when you see like these never-ending precisions, that's how we're getting nice integers in the answers. All right. But let's see, what's VT, right? For this one, I'm not going to calculate out, but I'm going to show you what I've noticed people have trouble with. All right. So I have a current source, right? And that's equal to 2 divided by the square root of 2 cosine cosine 10 t. All right. Now, that's being fed into this resistor, that inductor, and that capacitance. So really, if here's the current and VT and V is measured from here to here, in the picture it's measured right here. But remember, everywhere along this node is the same voltage. Everywhere along this node is the same voltage. So if I move VT just to the right, well, now you can probably see that VT is really the current times ZR in parallel with ZC plus ZL, right? You just got to find the equivalent. Now, in the other ones, you were given numbers, -5, +2, but here you're not, right? And you have to calculate those values. So you've got to know, all right, ZC equals 1 over SC equals 1 over J omega C, ZL equals SL. And what people have trouble with is, hey, what's omega? Well, in fact, it's right here, right? Because cosine is given in terms of cosine omega t, right? So in fact, omega equals 10 radians per second. All right, so now you know what omega is. Then you can calculate what ZC is and what ZL is. Then you can come up with the parallel combination. Now, the good part is, though, that you'll end up with a polar magnitude and magnitude and phase. All right. So how do you? So we have this current, and we have 2 divided by, I think, the square root of 2, right? Cosine 10t. Well, in polar terms, right, the magnitude is still this, right? But the phase is 0. Omega 10 equals 10 isn't shown, right? It's here. How do I know it's 0? Well, that's the true form. You have omega t plus or minus some phase. Well, since there's nothing there, it's 0, right? So if I'm going to multiply this phasor times, and I'm just going to say the magnitude of Z equivalent phase Z equivalent, right? I just have to multiply V equals 2 divided by the square root of 2 times the magnitude of Z equivalent, and then we have 0 plus phase Z equivalent. And then how do we go back to that cosine? Well, here's the magnitude. Right? We come back to our cosine 10t. Yeah, remember, the mega information is lost or it's not written down. You just have to keep track of it. And then you have plus right? I put 0 degrees here, but it's really the phase of the current source. It doesn't have to be 0, right? It might be something else. So at that point, then you can find out, and yeah, the magnitudes are all 2, the omegas are all 10, and the difference is really all in making sure you kept track of the phase properly. Okay. I just want to this is kind of the same, except they give you the numbers. Yeah. This one, again, you got it. I'm telling you, hey, omega is 40. All right, then you got to come up with the numbers for CL, ZC, ZLR, and then find the equivalent. All right. A lot of the DCs or op amps. I'm just trying to think of if yeah, there's the exponential polar coordinate system. I'm just trying to make sure there's no more complex numbers. Yeah. We got some Laplace and the math. Yeah. So really, I mean, I've pretty much gone over every kind of problem you'll run into in the complex thing. Yeah, then there's just, you know, manipulating things with exponents, complex, right? But what I notice is that people did well with the Laplace. And the RMS kind of thing. People tend to get that. And so I think maybe it's time next week we start doing quizzes. I'm trying to think. I know people want to come in with. I'll let you know if you actually have to be here for me to grade the quiz, because like sometimes it's great that I see a step, see a step. Oh wait, that's a misconception, right? Rather than just you got it right or wrong. All right. I'll let you guys know. Are there any questions? All right. Thanks for coming. What's your question? Oh, okay. All right. So what I do is I make. So the question is, what are these quizzes going to look like? Well, what I tend to do is just make up an exam and say, all right, today we're going to do 5 transients, and it's just going to be transients. So then we'll say, all right, then we're going to do 5 of these and 5 of these. That's pretty much what we do, right? But I generate them. This is the exam generator, okay? And the quizzes come from here. But yeah, working on those quizzes is studying for the 101 exam. It's a one-to-one correlation. Alrighty.